Good morning, good afternoon, good evening. Welcome to Coffee Break with Microchip Technology. Coffee Break is our ongoing forum in which we discuss new and evolving technology, all in about the amount of time it takes to drink a cup of coffee. I'm your host, Eric Glatfelter. Welcome again. With me in the studio today is Aliyah Fahoud. Aliyah, welcome back, and would you be so kind as to give our audience an overview of how they can interact with us during the live stream today?
Hi, good morning, and thank you for joining us today. We are currently live on YouTube, Facebook, and LinkedIn. And to participate in today's episode, you can leave your questions and comments in the chat or email us at livestream@microchip.com after the broadcast. And don't forget to follow, like, and subscribe to all our social media platforms. Thanks, Eric.
Thanks, Aliyah. Our topic today is testing phase noise in RF and clock designs. Joining us as our subject matter expert is Will Kurzwick, a product marketing engineer here at Microchip. Will, welcome to the program. Thanks for joining us today.
Okay, thanks for having me.
All right. So our topic today is all about phase noise. Would you start by giving us an overview of how phase noise is defined?
Sure, yeah, thanks. So, in the frequency domain, an RF signal at a single frequency looks like a perfect sine wave, oscillating back and forth, has the same period or phase for every cycle forever. But in the real world, you'll have some jitter, and the periodicity or the phase will fluctuate a bit over time. And alternatively, you can look at this on the right-hand side of the image, is the frequency domain. And ideally, an RF signal will just be a delta function. But in reality, the signal will have some bandwidth that bleeds into adjacent frequencies. And so this is often called the skirt or side lobes of the main carrier. And so here we're looking at just the upper half of the tone. And this is called single sideband when you look at one side. And so the amplitude difference between the main tone at any point on that skirt, that's the phase noise. And since it's a relative measurement from the carrier, uh, it's often referred to in units of or unitless value of dBc. And the convention is to measure it in increments of 1 hertz. So values are stated in dBc per hertz.
All right. So what type of applications are most susceptible to performance degradation due to excessive phase noise?
Yeah, satellite communications, LTE, and especially radar systems are reliant on reliable down conversion of signals. It has big impacts on weather forecasting, accurate navigation, and uninterrupted communications. So, phase noise performance of the local oscillators used in frequency mixing has direct impacts on system capabilities. And if it's not accounted for, you know, accurate data service and navigation just would not be possible at the same level of quality we expect today.
All right. What's the effect of excessive phase noise on this type of system?
So yeah, here's a real real world example. So any system where frequencies are being mixed down to a lower frequency for signal processing can be impacted. So in this example, we have a bunch of tones coming into a mixer on the RF port, and on the LO port we have our local oscillator. And so the mixer is doing its job. It's taking the frequencies from a higher frequency and down converting them to down to a lower frequency, so they get a bit closer together. And they also take on some of the characteristics of the LO, which is not always good. So this has the effect on the IF port there of essentially reducing the signal to noise ratio. So whenever this happens, it's much harder to resolve the individual frequencies, and it can lead to errors in signal processing and data loss.
Okay, we don't want any of those things. So, if a
No.
design if a design engineer or a systems engineer wanted to evaluate that and ensure that we prevented those sort of things, what are some of the methods that they could use to do that evaluation?
Yeah, so the most common approach is to use a spectrum analyzer because it's ubiquitous. It's in almost every research lab, university. Everyone's got a spectrum analyzer to look at RF signals and stuff and see what's happening. So oftentimes people will try to measure phase noise on these with a spectrum analyzer, but there are some drawbacks. It can be time consuming because you'll have to go back and forth by looking at your main carrier frequency and then looking down on the skirt and changing your measurement bandwidth and switching back and forth and making sure the amplitudes haven't changed. And not only that, the amplitude modulation and phase modulation are indistinguishable on a spectrum analyzer. So often they can still use a spectrum analyzer, but improve it and use a quadrature method. But this requires using a phase lock loop to lock your reference to your device under test. And there are some drawbacks there where the reference and the device under test must be the same frequency. So now you have to, if you want to measure multiple nominal frequencies, now you have to have a whole slew of reference oscillators in your lab to compare them against. So both methods, they have complex calibrations, and there's some other issues where you'll need to suppress the main carrier. And so this is a common issue with spectrum analyzer measurements where in order to get enough dynamic range, you'll need to use a high-pass filter or some other means to kind of bring down that main carrier tone in order to analyze the skirt of the signal. So when you do this, that's, all filters have some bandwidth. And so that kind of reduces how close into the main carrier you can inspect it.
Right.
And so it kind of limits your offset range there. So these measurements all suffer from poor dynamic range. And why? It's because your reference performance must be much better than your device under test.
Okay.
So the other approaches, which are not new, they've been commercialized since about the 1990s, is using a cross correlation method. And so, along with direct digital sampling, you can greatly improve your dynamic range. You can improve your accuracy. You can now measure in your close in phase noise. And the reason for this is because we're now, instead of measuring everything in the analog world, we're down converting the signals down to baseband where they can be inspected more closely. You don't have to worry about carrier suppression. And most importantly, you don't have to worry about phase locking your reference to your device under test. And so now this allows you to throw away all your reference oscillators. Now you can use a single reference oscillator and measure any frequency within that range. So it's really powerful type of measurement, and it reduces a lot of the calibration time and some user error.
Okay. So if someone was designing a analysis tool or system and they wanted to use the cross-correlation method, how would they go about implementing that?
Yeah, so we have kind of a diagram of how it works on a very high level. And essentially what you're doing is you have your device under test, which in this diagram is coming in on the left. And you want to split that and compare that on two measurement paths against a reference. And so by doing this, and in this case, you have two reference oscillators. And so by doing this, you can now use the power of cross correlation to differentiate between the common noise coming from the device under test, the common noise being common on channel 1 and channel 2, versus the uncommon noise, which is the unique noise coming from that first channel measurement path and the second channel measurement path, as well as your first reference and your second reference. And by being able to differentiate between the common and the uncommon noise, now you're left with cross correlation with just the noise from the device under test. So this allows you to really improve your dynamic range and measure things that you weren't able to do before with the same reference and device under test with just the spectrum analyzer.
All right. So I know we have a new phase noise analyzer. Can you give us an overview of the key features of that?
Sure. Yeah. So here's a really exciting product I want to talk to you about today. It's called the 53100A phase noise analyzer. And basically, all the engineering is done for you, and it is a cross-correlation direct digital phase noise measurement tool. And so now you can simply just plug it into a laptop and take world-class phase noise measurements without investing in a multi-box system or large spectrum analyzer-based systems. the 53100A's product that is designed for taking high accuracy phase noise measurements, plus or minus 1 dB. You can measure in very close to the carrier because everything is being down converted to baseband, so you can measure in millihertz from the carrier. There's no time-consuming calibrations. You can literally be taking measurements within minutes of powering on the unit. You don't have to worry about phase locking your reference and your device under test. And again, now you can have a single reference oscillator and measure everything from 1 to 200 megahertz in that range. Not only that, along with phase noise, it's taking phase difference measurements. So it's a frequency counter, and you can take other important telecom metrics and other important measurements like Allen deviation and MTI, etc. So it's a powerful tool.
All right, very nice. So if somebody's watching today and they would like to get one of these analyzers or learn more about it, how would they do that? Where would they go?
Okay, so go to microchip.com and type in 53100A, 53100A. And from there, it'll pop up with probably this product page here that we're showing, or there'll be some other documents that'll show up, and you'll have access to data sheets. You can download the sample software with some sample data files and just start playing around with the user interface and see really how intuitive it is and how easy to use it is. There's lots of help text with this software, and it's really powerful part that really complements the hardware well. And not only that, we have a whole bunch of app notes. So, from taking your first measurements to how to use dual reference oscillators to reduce your measurement noise floor, to another topic which we didn't talk about today, which is measuring microwave frequencies and higher frequencies beyond the range of the test set itself. So a lot of good info on microchip.com.
Cool. Well, it's an interesting topic. It sounds like a great tool with software and additional information. So, Will, thank you very much for sharing some of your knowledge and expertise with us today. Let's go to Aaliyah back in the studio and see if there are questions from our audience today.
All right. I do have a question here that we received via email. In your diagram, I was surprised to see 2 reference oscillators. Is this a new approach?
So it's not a new approach, but typically cross-correlation types of test sets come with a single reference input. So this is kind of a newly available commercial feature where now we're allowing access to both channels on the reference input. And so with the legacy designs with just the access to the single reference oscillator, it was great, but you had to provide a very high performance reference input. It had to have a lot of margin compared to what you're measuring against your device under test, 10, 20 dB in order to accurately measure your device. But what if you're trying to make really groundbreaking measurements on really high performance devices? What do? What type of reference do you use? So by using 2 reference inputs, now you can not only remove the instrument noise, but now you can, with cross correlation, you can remove the noise contributions from the 2 reference oscillators themselves, because they're both unique and they can both be identified and canceled out with the power of cross correlation. So there's no need to invest in really high performance reference oscillator like expensive double oven OCXO or hydrogen maser. You can just provide 2 pretty good reference oscillators, and you'll be able to measure down at the limits of the phase noise system.
All right. Thanks, Will. And I have another question for you that we received via email as well. What is the best type of reference oscillator for these measurements?
Yeah, so generally you want to have a reference oscillator with significantly better performance compared to your device under tests. So typically 10 to 20 dB are required in order to measure accurately your phase noise of your device under test. But again, this can be a problem if you are measuring a really high performance device under test. So that's what makes the 53100A a powerful tool, is because now you have access to apply to reference oscillators.
All right, and I have a question from LinkedIn. If the two references are of the same frequency.
Yes. Your two reference inputs should come in at the same frequency. Absolutely. Yep. That's a good question.
Let's see. And I have another question. How does this speed up measurement time?
Yeah. So we didn't really get into it too much, but part of the measurement process is one of the first steps is a phase difference measurement. And so there's a lot of interesting information in a phase difference measurement. And from there, the 53100A and other tools can essentially act like a high performance frequency counter, or where you can relay frequency difference plots or phase difference plots. And from there, you can calculate Allen deviation and MTI. And this all occurs essentially at the same time that the phase noise data is being acquired. So to the user, this is all being acquired in real time, and you can kind of track and toggle back and forth between the measurements using the time-lapse software that's provided with the unit. You can toggle back and forth and see how your measurement is progressing. Is it meeting a certain Allen deviation specification? Is it meeting a certain jitter specification? And is it meeting your phase noise specification? And all this data is being acquired simultaneously. So this really speeds up the measurement time, whereas opposed to a spectrum analyzer where you'd have to do phase noise first and then set up your test again and then try to take the other measurements. And spectrum analyzer, of course, cannot take frequency count type of measurements. So we're talking about clearing out your setup and moving over to a whole new set of hardware. So really saves a lot of hardware costs and measurement time and calibration time.
All right, well, it looks like those are all the questions I have for you today, Will, so thank you. And again, if we missed your questions, if you have additional comments, questions, you can email us at livestream@microchip.com. And don't forget to follow us and subscribe to all our social media platforms. Back to you guys.
All right, thanks, Aaliyah. Thanks again, Will, and most of all, thank you to our audience for taking some time out of your day to listen to the session today. Please visit us at microchip.com/coffeebreak. There you can see previously broadcast episodes. You can see our upcoming calendar, sign up for notifications, and add specific upcoming events to your calendar to ensure that you don't miss them. So thank you very much for joining us today again. Thanks. Have a good day.